All right, we're going to do another example here, and then we're also going to talk about another application of inductors. Here we have the power supply has been on for a long time, which again just means all the inductors are charged up. This is what is the energy stored in each inductor. And I've done this one on purpose here because we've got two inductors. Now the values I've chosen here are just, somewhat quote unrealistic, and just to make the computations a little bit, as far as the equations, a little bit easier. The actual answers might still be messy, but that's fine. Now, what we need to think about here is what is the energy stored in each inductor? And well, let's go ahead and just write down my equation for energy stored in an inductor. Energy stored in an inductor is 1/2 the inductance times the current squared. So we have the inductance, of course, for the two different inductors. We have a 1 Henry and a 4 Henry. So the only thing we really need is the current through each of those inductors. So we need current through each inductor. Okay, but we also know, since the circuit has been on for a long time, we also know that the inductors behave as shorts. One word. Now I'm not going to erase the inductors, but I'm just going to draw kind of a blue line through each of them here to indicate those are acting as shorts, because I need to find the current through them. Well, if I think about some of my analysis techniques that we've had, well, if I do mesh analysis, that gets me currents, like if I call this I1, and then if I call this here I2, we can clearly see I1 is equal to the current through the 1 Henry inductor, and that I2 is equal to the current through the 4 Henry inductor. So all we now have to do is figure out I1 and I2. And if we can figure out I1 and I2, we get their currents through those two inductors, which then we can go back and find the energy stored in each inductor. All right, well, let's just go ahead and start writing down some of our equations. So I'll start in loop 1 here. And if I do this, I get minus 12, because I'm coming in on the negative side of the 12-volt power supply, plus 10 times I1. Now, sometimes people want to say, oh, well, wait, there's this voltage VL here. But remember, that inductor, since it's fully charged, is behaving as a short, so there is 0 voltage across this inductor. So there's plus minus 0 volts here. So, okay, well then I just go past the inductor because it's acting as a short, and then I've got this 5 ohm resistor. So we got plus 5 times I1, and then because of the directions, I1 is going down, I2 is going up. They're going in opposite directions, so it would be I1 minus I2, and that this is equal to 0. Now cleaning this up a bit here, we would get then, I'm going to skip some of the algebra steps, or skip showing some of the work. 15I1 minus 5I2 is equal to 12. And then for loop 2, well, there's similar kind of argument here. If we start with the 5 ohm resistor, I'd have 5 times I2 minus I1. And then what would we have here? Well, we'd have 15 I1, and that's, I'm sorry, not I1. I2, and that would be equal to 0. Because again, the voltage across this inductor here, since it's been on for a long time, is fully charged, is 0 volts. So it's acting as a short. And then simplifying this equation, we get minus 5I1 plus 20I2. And this is equal to 0. Now, I'm going to just pause the video here for a second, plug this into my calculator to solve for I1 and I2. So after plugging it into my calculator, I got I1 and I2, and they're not pretty numbers, but that's okay. I mean, pretty meaning nice round numbers. I mean, they're not ugly. I mean, what does it mean to be an ugly number anyway? I get 873 milliamps for I1, and then for I2, I get 218 milliamps for I2. And then again, this is then the current that's going through the 1 Henry inductor, and this is the current going through the 4 Henry inductor. So then at this point we just have two further computations, pretty simple ones, where we use the formula up here, the top, for energy. So the energy stored in the inductor is 1/2, and this would be, and I'll say this is for, let me make sure I make this energy for the 1 Henry. 1/2, 1 times 873 milliamps squared. And make sure that you're doing milliamps squared and not like 873 squared. And when I do this, I wind up with an answer of 381 just 381 millijoules. And then if we do the energy stored in the 4 Henry inductor, we get 1/2 times 4 times 218 milliamps squared, which is 218 milliamps squared divided by 2 times 4, which is 95 millijoules of energy stored in that inductor, in the 4 Henry inductor. Now, some of you might say, well, wait a minute. Earlier you said that the larger the inductor, the more energy it can store. And that's true. The larger the inductor is, the more energy it can store. But that doesn't mean that just because you have a larger inductor in a circuit, it's going to store more energy. You have to do circuit analysis, because even though this 4 Henry inductor is larger, the key thing to remember here is that it's got a much smaller current going through it. In fact, the current going through I1 is roughly 4 times bigger. Well, if it's roughly 4 times bigger, that means I'm going to be doing 4 squared, so that means that this is going to be, this number here, let me circle it, that means this number here is going to be roughly 16 times bigger than this number here. And if this is 16 times bigger than this one, I'm only multiplying by 4, so this, basically, just doing this sum of this arithmetic in my head, I should roughly be getting 4 times as much energy stored in the 1 Henry inductor as in the 4 Henry, which is roughly what I'm getting, not exactly. And that's just because of the fact that there's so much more current going through the 1 Henry inductor than there is for the 4 Henry inductor. Now, if they had the exact same current going through, like if each of them had 1 amp of current going through, then clearly the 4 Henry inductor is going to have more energy stored. But ultimately, you want to just make sure you understand the equations and make sure you do your computations correctly to get to the correct answers. Now, one final thing I want to do here to kind of finish up another application of an inductor, and this is something that depending on the type of cell phone you have, you're already doing this. And these are present everywhere. So what I'm going to do here So I'm going to draw an inductor. And I'm going to draw another inductor. And I'm going to draw it I'm drawing it close to this. Now this right here, and we're not going to talk about it in detail right now. We will talk about it in a lot more detail in the next course, and the course that follows this, is that this right here is what's called a transformer. And sometimes what they'll do is they'll put two lines through here indicating it's an ideal transformer. And I'll just real quickly show you one of the things it can do, because often you'll see a transformer and it might be something that's called like a 10-to-1 transformer. And that has to do with what's called the turn ratio. But what that means is we can use transformers to step down voltages or step up voltages. So when you're looking at your cell phone, for instance, when you're charging it, cell phones charge off of 5 volts and a couple amps, like 5 volt 1 amp or 5 volt 2 amp. That's what cell phones charge off of. Now we've got 120 AC coming out of the wall. Now we don't work with the 120 AC and make that DC and then step it down to 5 volts. What we do is we first use a transformer to step that 120 volt AC down to a much more reasonable AC voltage. Maybe we step it down to 12 volt AC. And if we step it down to 12 volt AC, which is what this would do, a 10-to-1 would step it down to 12 volt AC. If we step it down to 12 volt AC, then we might convert it to DC and then step it back down to 5 volts. Now, one of the things I wanted to talk about is this is actually, these coils here, it's a transformer, but inductors are used / critical for wireless power transmission. And this is, again, something some of you might have. You might have a cell phone charger where you just set your cell phone on top of the charger. You don't have to plug it in. It's a wireless charger. And what it is that base that you're setting it on, so this base here, there's a coil inside it. And then you set your cell phone on top of it. Has another coil. And basically what happens is when you bring two inductors close together, even if they're separated by air, or in this case air, metal and plastic and other things like that, it doesn't matter, because what ends up happening is when you run an AC signal through this, it generates a magnetic field which will induce a current in another coil, and that's how we can get a charge. Now this has a lot more applications than just cell phone chargers, though. There's a huge application of this in the medical industry. And I'm familiar with this one because I'm familiar with some of the medical devices, but actually I use one of them myself. I've got a peripheral nerve stimulator implanted, and I have a rechargeable battery pack implanted in my chest. And to recharge my battery, I lay on my chest. There's a little wire coming out here. And it's like, it's got a rubber coating, I think, some kind of rubber or plastic coating on it. But it looks like a giant washer is what I put on my chest. But really what's going on here is we've got a bunch of wire that's just coiled around in here and then comes back out through that. And I'm really just literally setting a coil of wire on my chest. In other words, I'm sitting an inductor on my chest, and that inductor is then coupling with the inductor that's inside the battery pack that's inside my body and wirelessly charging it. So the battery pack inside my body is getting wirelessly charged because of inductors. So that's a key application of inductors. And we're not going to touch on that really too much more in this course. We will come back to it again, and you'll probably hear me even talk about the same application again, because one, I think it's cool and amazing, that you're basically, I'm able to charge a battery that's located inside my body, and not actually have to have any literal, like, kind of, I always joke, like USB connector on my body. I mean, it's literally inside my body and it's just being charged through air. But it's the same technology that is used in cell phones for wireless charging for cell phones. All right, so we'll end here. And the next thing we're going to talk about, though, is when we have multiple inductors and capacitors in a circuit, there are ways to get, just like we have with resistors, we can get equivalent inductance and equivalent capacitance. So that's what the next lesson will be. And then after that, we will get into some other circuits with inductors and capacitors, which will actually kind of wrap up this course.